Okay, I think just phone had technical difficulties for a second. Apologize. Okay, cool. All right, resume, sorry. Okay, we've done LUMO, HOMO. Those have been identified, so we're good on those. Now we have to do excited state. Excited, like I said, you added photochemical energy, which is a fancy term for I basically excited an electron with light. That's all it means. And so one of the electrons from your HOMO, which after you've identified in ground state, makes your life so much easier. So keep your electrons kind of consistent for the first row. So we have 2. We're going to go up, filling them in with however many have. We have 4 at the beginning. We have 2 now because we've already filled up the first level. And we said that one for excited, one of the electrons from the HOMO of ground moves up 1. That's the key. One of the electrons, so we're going to keep 1 and we're going to move 1 up 1 level for excited. Therefore, your LUMO now switches to 4 because he is the lowest unoccupied out of all the 4 levels anyway. 4 has none of them, so therefore 4 becomes the lowest unoccupied molecular orbital. That's this guy. HOMO now switches. He used to be 2 in ground state, used to be level 2. Now he's going to be level 3 because if I go up, 2 does have 1, but there is a level higher that still has 1, which is level 3. Therefore, he is the HOMO of excited. And you will see that this is a common trend. The HOMO and the LUMO of the ground state is lower by 1 in the excited states. Both of them are lower in 1 level than the excited states. So that's a pretty easy point of reference as well. So the HOMO here, though, has only 1 electron. The LUMO has 0 always. So, you know, that's fine with that. But that's essentially all you need to know for orbital theory. You won't have to know, oh man, these guys have to do this and then this. And don't worry about that. That's a more of a conceptual thing, but it is important to understand, but you don't need to know for the sake of the exam. And I don't believe you do. I don't believe you do. So that's orbital theory understanding. And then timestamp on this one is 2 minutes. 06. Oh yeah, well, that's gonna be a little bit confusing. Unfortunate. Okay, but regardless. Okay, so we can. All right, I'm being a little bit unorganized here. Okay. Now, we are going into Diels Alder. So Diels Alder, I can't speak. Diels Alder. Biggest thing, if I was to restart, okay, let's restart from this one, and I will send a picture of what I meant by that little tip sheet in the beginning. Diels Alder reactions, so what the basis is that you're always going to use a diene. So they always use a compound with 2 alkenes, also known as a diene. And this diene has to be in cis form. What does cis form mean? Example. This is cis. Both of the alkenes are facing the same kind of direction. They're both facing here. An example of, are you serious? Oh, my phone is just being cranky, I guess. Apologies again. Okay. This is an example of cis because both the alkenes are pointing at the same direction. I have a trans now. Both alkenes are pointing in different directions. So trans, not usable. If I have a compound with 3 alkenes, if I was to draw this like a 7-membered ring, not usable. Has to be 2 alkenes, not 3. 3 alkenes? No, I can't have that. So that's the first requirement. If I don't have those in that kind of like, this is the basic form, right? This is the basic form that you usually see. If it's not in this form, can't be used, and it's not referencing Diels Alder if it has more than 2 electrons. Okay, that's the first key. 2, so what is a dienophile? Dienophile is basically the compound that attacks from below, generally, attacks below, and causes formation of a hexagon or hexane of a hexane. That's the key. Whenever you're doing any of these reactions, and usually the diene, the basic form of a diene is just this kind of double bond. That's all it is. That's the basic form. So basic form without any external or internal branches. Basic form without anything added to it. Now, what was I going to say? Dienophile of a hexane. Yes. So whenever you do this, if it makes sense to you guys, hopefully, whenever you're adding this, the way that your arrows are essentially attacking each other is the top carbon is going to attack the top carbon of the diene. So the top carbon of the diene attacks the top carbon of the dienophile. Then you kind of move in a cyclic motion. The bottom carbon of the dienophile attacks the bottom carbon of the diene. Then this double bond has to move inward, because obviously the flow of electrons, you can't have a carbon that has two double bonds on both sides. You can have accumulated, but it doesn't function in a ring like that. That's not what it does. So once you've created this, these, I'm going to put little circles on them. This is the bond you've created. This is a bond you've created. And then you've created this one. You've created this new alkene. It's the essential part of how this mechanism works. So it kind of, and I'll send a picture of this in the thing, but this is essentially how it would work if you would use the first example on the group work. So you're creating top to top, you're making a bond from top to top, bottom to bottom, and then this rotates, and then these are the new bonds that are forming. That's how a cyclohexane is always being made. That's the reaction mechanism. Okay, so hopefully that makes sense. Now, after you've understood that this is the basic of what it should be made, that's the main compound that should be made. Anytime you see any kind of Diels Alder, and I'm just going to give you guys an example just from the group work, we're just going to do just the first one. So anytime you see, oh, this, your thought process is, plus, I'm going to do CHO, which is, CHO is just a fancy thing for an aldehyde. Don't be too intimidated by these. These are just aldehydes, but I'm pretty sure they're just out of convenience. First step, number one, is it cis? Pointing the same direction? Yes, you're good. Two, what's it called? Cis is good. You don't have to move anything. Yep, you're fine. Diene, so, okay, yes, so now that takes you into the second part. Once you've examined this, you have to examine, you've examined the foundational structure, right? The foundational structure, just this. Now you have to see if there are any external or internal groups that are on here. Now, a key, the external and internal groups will only be on carbons 1, 2, 3, and 4. So this kind of brings you back to the thermodynamic, but you're going to number your carbons 1, 2, 3, 4 in whatever manner. It doesn't matter really, just as long as it's not confusing to you. But note, it's supposed to be star, carbons 1 and 4 only have the external/internal groups or branches or whatever you want to call them. And so once you've seen that there's nothing, so I see, like, say for example, I had a methyl out here and then methyl out here, yes, now you would, but in this case you don't, so there's nothing, so you don't have to examine those. But general rule for the external groups, for you not to be confused, and I see that sometimes there's like enantiomers that are placed in the group work, so sometimes those are in the clickers. I understand that, but for the sake of you not getting confused, place external groups, etc. So how I would show this to you guys would be, let me show you an example. External groups, boom. External, meaning he's pointing outward to the ring, okay? That's what external refers to, pointing out of the ring, point, I can't spell point for some reason, point out of ring to be, essentially the ring to be, yeah. It's not a ring yet, but obviously it's going to be. They are gonna end up on dash. They're gonna end up on dash, on the product, Internal groups, point inward with relation to the ring, obviously, with relation to future ring. So hopefully that is readable. Okay. Now, internal, example. Internal, both of these groups are internal, pointing inward to the ring. Okay, internal. These guys always end up on wedge. Now, oh, Mohammed, sometimes you see in the group works, oh man, some of these guys, they point, oh, this one is actually on wedge, this one is on dash. Why that happens is that enantiomers are made, right? So the enantiomer you'll probably see will have these guys both on, like the external groups, or external will both be on wedge, and then you'll have different notations for the dienophile. But for the sake of convenience, please just memorize it as external is dash, internal is wedge. Enantiomers, you'll flip everything anyway, and you'll see the ease of it. So it's not too bad. So you've identified external, internal, and resulting stereochem. Now, 3. This one, dienophile. So analyze your dienophile now. essentially cis or trans. Now, cis or trans for symmetric, for double substituted alkenes, okay? So cis or trans only for double substituted alkenes. What I mean by this is sometimes you'll see the mono substituted. So the double will look like this. We'll just put CHO, CHO. They could also just look like this, which is just cis. So this would be trans. This applies because it is double substituted. We have two different branching groups on the alkene. This also applies, it's cis, you know, so double. This guy is mono, so no. Mono, therefore not cis or trans. So mono, no cis or trans, okay? Hopefully that makes sense. So I've identified on this guy that this is trans, correct? Because both are facing different directions. If it was cis, they would both be the same direction. Now, whenever you do cis, what I would suggest as well, cis, usually both dashed, okay? On the final product. Cis on dienophile, remember, you need to be consistent with what you're looking at. Dienophile, this one was the diene. Okay, good. This is also the diene. We're going to keep this on the diene. Dienophile, dashed on product. That's for the cis. Trans, doesn't matter, obviously, 1-1. So 1 dash, 1 wedge. Whichever one you do, it doesn't matter. It doesn't matter whichever one. Like if you do the top, if this one, say for this one, if this one's on a wedge, if this one's on a dash, if this one's on a dash, if this one's on a wedge, it doesn't matter. So that's okay. Now, so walk through the problem real quick. Let's kind of just, I've already done it before, so it's probably easier just to explain it here. So as you can see, I basically just kind of went through the arrows, top of the diene, top carbon of the dienophile, they attack each other, cyclic motion, bottom to bottom, alkene moves, you've created this, which essentially you've created this guy as the basis. This is the basis now. Then you've identified, oh, this dienophile, I've already identified that the diene has no external groups, so nothing off of these carbons, nothing off of here, nothing. And then these guys were trans. Therefore, one's on a wedge, and one's on a dash. That's why those are on here. And you have to be careful because remember, like I said, 1 and 4 carbons, they have external groups, etc. 2 and 3 though could have their own branched groups. Like that's a thing. But 2 and 3 are not on any stereochem. Why? That's whenever you notice like any problems. 2 and 3, no stereochem, because this sp2 alkene that you make with the cyclohexene technically, this does not permit stereochem. So general rule, carbons, let's say, just to draw an example's sake, carbons 2 and 3 cannot have stereochem, and by stereochem I just mean wedge or dash. Okay, they can't, because sp2 carbons generally they can't. They're too fulfilled, so they're not able to at all. These 1 and 4 can because they're sp3. These are sp2. Okay, alkene bonds cannot. Alkane yes, alkene no. Okay, so alkene no, alkane yes. Okay, sp2, sp3 carbons. That's why you never see any stereochem on these guys. You'll see stereochem on 1 and 4 because yes, and you'll see stereochem on 5 and 6 as well, which is basically just the 5, 6, which is from the diene. Yes, you can because it's not alkene. Now, there are problems though. Well, you have a dienophile that's a triple bond, okay? So say you were given the exact same compound, but you were given like, oh, actually this is a different compound, but that's fine. For the sake of example, it's okay. I'm gonna add something here though, because I want to show something with that. We're gonna do plus a, just do something simple, keep it pretty, let's do this. Now, this is a triple bonded dienophile. Rule, triple bonded also cannot have stereochem. They can't in general. Now you're thinking, oh, well, it's not going to be it's not going to be triple bonded whenever you do the product. That's true. So if we're going to take this, pretty simple, basically. Now, oh, you also might not see, oh, no, there's not a top carbon. There's not a, well, this is a little bit of a special case because it's a triple bond, but just stick with your symmetry, stick with your cyclic motion. Don't confuse yourself. You would just do this. Then the next carbon comes up, attacks the bottom carbon, and do here, okay? Just keep it cyclic, keep it simple. Now, draw your base of what you will always make. You will always make a cyclohexane or hexene, but remember, you have to add the groups. You always make a cyclohexene, but you have to add the groups that were on all the associated carbons, right? Okay, so you have to be consistent. So from here, right, you have to add now from this basis that is always made, you have to add exactly what is on the carbons. So one actually has an external methyl, meaning he's going to end up on dash. So I'm going to draw a dashed carbon. 1, 2, 3, 4. Carbon 2 and 3, they have methyls. However, they have no stereochem because an alkene is present, and that's always present whenever you're doing these kind of things, these kind of reactions on the Diels Alder. That's good. 4 has no external or internal groups, therefore he has nothing. And then 5 and 6, I'm going to label this guy 5, this guy 6, because of the way I'm kind of went cyclic, and also the way that it kind of like presents itself. 5 and 6, they're not cis or trans because it is triple, so you don't have to worry about whether or not that. And also because it's a triple bond, all I've done to add a bond, basically whenever I'm adding this, instead of it attaching like this on the cyclohexane, essentially, it attaches with a double bond that's still present, okay? So, actually, we're gonna remove this carbon. Hopefully that's gonna be, oh, yeah, you guys can see that, hopefully, yes. Okay. Sorry about the other, I did not mean to have the background. Boom, boom. You've left with this alkene, therefore the alkene has to go back into here, because whenever you're doing this, you only use one bond. That's why whenever I go from an alkene on, like, say, this guy, he resorts to just a single bond here, right? Because I only have an alkene, and then you lose one of these bonds, becomes a single bond. And then from a triple bond, I lose one of these bonds, and he becomes an alkene. Alkenes, sp2, cannot have stereochem. Therefore, both of these aldehydes are on just regular bonds with no stereochem. That'd be the answer for this one. And then the last part that's pretty important in terms of enantiomers and meso compounds, when you're looking at meso symmetry, right? This is not a symmetrical compound, not symmetric. Therefore, he has enantiomers. If he's meso, he would be completely symmetric, and he has, what's it called? He has enantiomers. Therefore, if it's meso and he's symmetric, he will not have enantiomers, because you essentially, like, say, an example of a meso will be like meso compound. It'd be like this. This would be a meso compound. Boom, completely symmetric. Therefore, just this is the only final product. No, you're not gonna do this. You're not gonna make the enantiomer because he's symmetric and he can be imposed on himself. You can do like a mirror image and it's the same thing. This does not exist. No enantiomer. Hopefully that makes sense. In the case that it is asymmetric, you can make the enantiomer. And so we can make the enantiomer, and the only thing that changes is this stereochem. So you would just have another product plus this dude, and then this dude, OH, oh shoot, OH, okay, cool. There you go. That is the basis of Diels Alder, right? So just to kind of recap, external groups on the diene go onto a dash, internal groups on a diene go onto a wedge. And you're only going to look at the groups that are on 1 and 4, but the groups on 2 and 3 have to be added, but they're not the ones with stereochem. So on carbons, 2 and 3 is what I'm referencing. 1 and 4 do have stereochem, 2 and 3 do not, because there's an inherent alkene. The alkene between 5 and 6, though, may or may not. Depends if there's a triple bonded dienophile. Triple bonded dienophile means I produce an alkene between 5 and 6 on the final product. So therefore, you don't have any stereochem. Anytime you see, let's see,